free body diagrams. There's nothing new here. F equals ma is the only thing in the whole unit. What we're doing now is doing vectors in all the possible dimensions, all the tugs and pulls and pokes we can do at an object. In the end, we have to calculate the sum of all forces, sigma F. This can be written as F net, F total, and F unbalanced. I like using the sigma F on the left because it's a very common math notation you will become familiar with. Net and total are acceptable too. I'm not fond of unbalanced because it takes a lot more writing to do, and it is a product of the high school system only. I gather that whoever came up with the idea was to say this is like a tug of war, and whoever's got the leftover force is unbalanced. So if we look at these two, it's unbalanced to the right, but I've never been fond of that terminology. I much prefer this over here, but it just doesn't matter. If people have changed the style, what they're talking about is the same thing. This is Dr. Doolittle's Push Me, Pull Me. It's an animal that's tied together at the waist. I have horrible nightmares as a kid that if this one had to go poop, did this one have a horrible fate in store? But in any case, you can see that the vector forces on this animal would be problematic. You can also consider this to be a symbol of our governmental systems, where we have the left wing and the right wing, and what gets accomplished is between liberals and conservatives pulling in opposite directions isn't very much. So let's say we have 80 newtons to the left and 100 newtons to the right. Obviously, the right side is winning, 20 newtons more. And that's what some teachers would call the unbalanced force. We could also write it this way, right? 80 newtons to the right, 100 newtons to the right. Now we'd have 180 newtons to the right. It's really quite simple to see whether forces are helping each other out or fighting each other. We have a net force of 20 there, and on this one we have a net force of 180. Some teachers will call it F unbalanced. In order to do a free body diagram, what we do is draw the diagram, put the forces on it, and calculate the sum. If you add up numbers, you call it a total. If you add up vectors, they call it a resultant. And we talk about resolving them, which is basically the same as solving them. This is just done to remind you to include direction. The two forces do not cause two accelerations. The forces have to be resolved first, and whatever force is dominant, the leftover force, is what causes acceleration. You must not calculate separate accelerations and average them. Even if it will give you the same answer, it's factually incorrect. So we need to resolve our forces first. There's our total force here. And that's the one that will cause the acceleration you see. So you take the total force, divide it by m, and you'll get your acceleration. You do not attempt to calculate the acceleration from separate forces. Let's try a simple example. A mass of 10 kilograms is subject to 100 newtons up and 150 newtons down. Calculate the object's acceleration. You draw your free body diagram with the two forces on it, two arrows. You can set up this system right here that I've shown you. You have this graphic on all your worksheets. You can set it up and go through it like clockwork. We need to establish our directions to get rid of the vector notation. So we'll call up positive and down negative. And then it becomes very simple. Say 100 newtons, add it to minus 150 newtons equals negative 50 newtons. We put the direction back on. The total force is 50 newtons down. That's the net force, the total force, the unbalanced force. It's all the same thing. In the equation over here, I could put 50 newtons down for the sum. I put 50 newtons in the formula. We divide by the mass, and we get the acceleration of 5 newtons per kilogram. And you go, that's weird. Isn't acceleration supposed to be meters per second squared? But when I did this formula, A equals F over M, I get newtons per kilogram. It is meters per second squared. It's just been hidden on you. Okay? We'll see in a moment that newtons per kilogram is exactly the same as meters per second squared. And I harp on this fact repeatedly in these videos because it will make things much easier to comprehend shortly. And it's easier to write down. So let's take a look at it this way. You're supposed to get acceleration in meters per second squared. But this formula just said newtons per kilogram. So our expectation was that A should show up like this. And instead, when we solve the formula, we got these units. And that doesn't seem right. But they are, in fact, the same. Watch. If I write newtons per kilogram, and I expand what a newton is really hiding, which is mass times acceleration, we can see a cancellation happens, and in fact a newton per kilogram is in fact a meter per second squared by definition, because a newton is a derived unit. It's hiding mass times acceleration already. Why then do we write newtons per kilogram? I would encourage you to leave accelerations in newtons per kilogram, and you'll see why in the next day or two. It's a great way of removing misunderstanding, and I do not think it's emphasized remotely enough in the textbooks. Here's a second example. A mass of 10 kilograms is subject to a 100 Newton force up, and we know it has a 20 Newton force total downwards. So I'm not telling you the two separate forces, I'm telling you the upward force, and I'm telling you the sigma F, the total. And I want you to calculate its acceleration and the missing force. This would be like saying Sally and Jim are contributing money. Sally gives $50, Jim gives $100. How much money did they collect? That's easy. But if I said Sally and Jim chip in some money, Jim put in $100, there's $150 on the bowl, so how much did Sally put in? That's all we're doing here. We already know the net force, so we can calculate the acceleration without it. Let's say the question only asked calculate the acceleration. It didn't ask this part. You'd realize you didn't need this number at all. Once you have this number, you can go ahead and use Newton's law and calculate the acceleration. 2 newtons per kilogram, which is 2 meters per second squared. Now, the other part is ridiculously easy. 100 positive plus what equals negative 20? Well, 100 up against 120 down would leave me with 20 down. Or you can write it out formally. The sum of the forces has to be all of them added up. And we can then figure out F2 is the total minus F1. 20 newtons down minus 100 newtons up. I get minus 120 newtons. Right? Do you see the substitution I did? Up stays positive and downs turn negative by the convention we set up. And there it is in pure algebra, the answer that common sense would lead you to. Here's a third example. A mass of 10 kilograms accelerates at 10 meters per second squared down, and the second force, F2, is 300 newtons down. So what's your total force and what's F1? Now you're not calculating acceleration, you were given the acceleration. So you're not setting up A equals F over M, you're going to use F equals MA. But we need to add up the individual forces first to get this. Except when we look at this, mass times acceleration, we already know the total force. It's going to be 100 newtons, m times a. When I do m times a, formally over here, I get 100 newtons down. So the total force is 100 newtons down, and we said this was 300 newtons down. So this plus that equals 100 down. How do we solve for it? 100 newtons down resulted from 300 newtons down plus what? 200 newtons up. 200 up plus 300 down would give you the 100 down that the behavior showed you was there. So example 1 and 2 are the same. Example 3 is slightly different. Here are 1 and 2 force examples. A 5 kilogram object is subject to a force of 100 newtons right. Calculate its acceleration. That would be your free body diagram. And you just do this. Force over mass is 100 newtons right divided by 5 kilograms equals 20 meters per second squared to the right. I put the units in blue again to try to make you see the units separate from the direction. These things start to get a little bit busy, but don't be intimidated. And I put the vector signs on here very faintly because, again, these things can get really busy. So if you find them getting busy and I say, please include the vector signs, you can put them on after. A 5 kilogram object is subject to 100 newtons right and a frictional force of 35 newtons left. Calculate its acceleration. So now we have two forces on the free body diagram horizontally. 100 newtons to the right, 35 newtons to the left. And the mass is 5 kilograms. We always start the vectors from the center of the object. We don't put them on the edge. Bring them right to the middle. That's typically how it's done. To calculate the acceleration, we need to get the sum of forces first. So we're going to cause this direction positive and this direction here negative. I just make a little statement, or you could just draw it on here. This means we have 100 newtons plus minus 35 newtons equals 65 newtons. Why didn't I just write 100 newtons minus 35 newtons? Avoid it. Add them. These are addition of positive and negative integers. So plus a negative is totally acceptable. It will cause you grief later if you don't do it that way. And we get an acceleration of 13 meters per second squared. So that's as complicated as the horizontal ones get until we start pulling at angles. Finding component forces from the total. A 5 kilogram object is subject to a force of 2100 newtons to the right and is accelerating at 11.3 meters per second squared to the right. Compute the second force on it and the total force. Having been given mass and acceleration, you can already compute the total force without reference to the other two. The total force would be 5 kilograms times 11.3 meters per second squared, or 56.5 newtons to the right. If you know the total, and the total is now made up of 2100 newtons to the right and a force to the left, what would that be? Well, the sum of forces is F1 plus F2. So the second force would be the total, subtract force 1. 56.5 newtons to the right minus 2100 newtons to the right, which is 2043.5 newtons to the right. Negative to the right, so that would be to the left. That's pretty much straightforward. We try a variation on this problem. A 5 kilogram object is subject to two forces. F1 is unknown and F2 is 100 newtons to the right and accelerates at a 50 meters per second squared rate. Once again, enough information was given for you to calculate the total force right from the acceleration value. So the total force is going to be ma, and that is composed of F1 and F2. So the unknown force will be ma minus F2. ma is 50 times 5. Then we subtract 100 newtons, assuming that we've made positive to the right. So we get an answer of 150 newtons, and since positive is to the right, this is 150 newtons to the right. This is doing it with fewer steps and is acceptable, but it may cause you a bit more confusion than the way I did it on the left. There's our answer for F1, and at this point, a little warning bell in your brain should be going, meet, cognitive dissonance. This is a phenomenon like writing the word yellow in the color of blue. Your brain goes, conflict, conflict. Do you see a problem with me writing 150 newtons to the right at the vector F1? This vector is clearly pointing to the left. And you might go, I've made a mistake. No, you didn't. I've never seen free body diagrams set up that the vectors are pointing in the same direction. This is a double tug to the right. This is two people pulling on the right. It's not a push me, pull me problem. The diagrams are never done to scale, and if they swung the vector around to the right, they would already be hinting at the answer. So you will frequently see answers that are in conflict with the drawn vectors in the diagram. Two more examples and we're done. A 5 kilogram object is subject to a 100 Newton force to the right and is accelerating at 10 meters per second squared. Once again, we can calculate the total force without reference to the components. And then we solve and we get 50 newtons to the left. A 5 kilogram object is subject to a total force of 200 newtons to the right and a frictional force of 35 newtons to the left. Calculate its acceleration and the applied force. What do I mean by applied force? That is often referred to as like this is the kid tugging his sleigh and the frictional force is 35 newtons. I am not going to make you write down FAPP means applied. Learn it like you learn the English language. You just pick up words as you go. So the applied force would be what we would have called F1 and F2 before. Doesn't matter. Since we know the total force, we can work backwards and calculate the acceleration. We'll decide that right is positive, left be negative. The sum of force was given at 200 newtons to the right, so the acceleration of this object should be sum of force over mass. 200 newtons to the right over 5 kilograms gives us 40 meters second squared to the right. What is F applied? This is what we can do by inspection. I mean, look at it. There's 200 newtons total to the right. There was 35 units of drag on this problem. So how hard did this kid have to pull? He has to pull 235 because you're going to lose 35 to friction and you need to have 200 left over. So that one is by inspection. The important part about free body diagrams is there is nothing new here. This is just Newton's second law with a diagram thrown in, and you're being asked to add up the forces or play with forces in different directions, but it's not new ideas, concepts, or formulas. Like many diagrams, like Lewis dot diagrams in grade 10, they can look frightening when you see a complete one, but if you jump in and try them yourself, you'll eventually realize, oh, I can't believe I ever did my problems without diagrams.